This section's pretty long, isn't it? Oh well, let's keep going. Objects that are not supported and are only feeling the force of gravity move with an acceleration of 9.80 meters per second squared downwards. And this is for objects that are near the surface of the Earth. So if I were to drop my marker while my marker was falling, this would be its acceleration, 9.80 meters per second squared, because my hand wouldn't be holding it and the floor wouldn't be supporting it yet because it's still falling. And I'm going to say that while my marker is falling to the floor, air resistance isn't going to be that big of a deal. My marker was never going very fast. What if I was to throw my marker upwards? And basically, I just give it an initial velocity upwards. But once it leaves my hand, it is no longer being supported by my hand. It's not touching the floor yet. Air resistance can still pretty much be ignored. The acceleration is still 9.80 meters per second downwards. This is really just what gravity is doing. So this rate is just what gravity is going to try to do to objects if they're not feeling any other forces, no other pushes or pulls. In these cases where this is true, it's called free fall. So this is actually called the free fall acceleration. We use this value, 9.80 meters per second squared, so many times that we gave it its own little abbreviation, little g, 9.80 meters per second squared. So I imagined a ball being thrown up with a certain velocity, and I picked 19.6 for a reason. Just go with me for now. So its initial velocity at a time of 0 seconds when I start my stopwatch is going upwards with that velocity. 1 second later, it will be going slower because gravity's been working against it. So 1 second later, it'll only be going 9.8 meters per second upwards. Another second later, gravity would have been able to bring it to a stop, so it'll just hesitate for an instant and kind of hang there at 0 meters per second just for an instant before it starts to accelerate and speed back up here. And when my stopwatch says 3 seconds, it would be going 9.8 meters per second down, which I suppose you could also call negative 9.8 meters per second. And 1 second later, it would be going 19.6 meters per second down. The velocity changed by 9.8 in here, and then here, and then here, and then here. Each 1 second gap, the velocity changed by 9.8. So this ball is in free fall. Air resistance doesn't matter. There's nothing else pushing or pulling on it. But here's the weird part. It's in free fall even when it's moving upwards. We don't use the word free fall to actually indicate falling. We use the word free fall just to indicate, and the only force pulling on it is gravity. Free falling doesn't mean that the object has to be moving downwards. It does mean that the acceleration is always downward. So for this whole time, every single teeny tiny instant in here, the acceleration would be 9.80 meters per second squared downwards the whole time. For us, we're going to stick to some simple situations. So here's our kind of our simple setup. We're only going to look at situations where the acceleration is constant. So the acceleration is just going to be equal to the average acceleration, just because it's the constant value the whole time. Right? And we're also going to stick to cases where the motion is only along a straight line right now. For these cases, this equation is true. The final velocity is going to be equal to the original velocity plus the acceleration times the time. Just make sure that you do this multiplication before you do the addition there. Also notice that this has units of meters per second squared, but then you're multiplying it by a second. So then that as a whole term here, this should have units of meters per second. Right, so that way when you do the addition here, you're adding apples to apples, meters per second to meters per second. Now, some of you might not have had algebra for a while, so I thought I'd do a quick rearrangement of this equation Like, what if you needed to solve for this, the original velocity? Or what if you needed to solve for time? How do you rearrange this equation? So here I rewrote the equation that we did up there, but I left a big gap around here so I can add and subtract some stuff. So I want to solve this equation for V original. So I want to get that by itself. So I've got this term over here added on to V original. So I'm going to subtract that term from both sides. So minus AT minus AT. Right. Then this would go away. So then that would leave us with the V original is equal to V final minus AT, which I've just rewritten down here. Let's start with the same equation, but say now I wanted to solve for A, so I want to try to get A by itself. I want to get this V original to the other side, so I'll subtract that term from both sides. Minus V original, minus V original. So that will cancel off from the right side. And then I'll have VF minus VO is equal to AT. So that's why I had here in black, VF minus VO is equal to AT. But then I'm still trying to get A by itself, so I divide both sides by T. And then that can cancel out there. There you go, solve for A. If I was trying to solve it for T, start with the same equation, try to get T by itself. So first I'm going to get that V original term to the other side. So subtract both sides by V original, which means that they will cancel out over here. So I'll get a VF minus a VO is equal to an AT. Right? So I had that in black over here. But then to get T by itself, divide both sides by A. It cancels out here. So then we end up with VF minus VO over A is equal to T. For all of these equations, we would call these kinematic equations, equations of motion. If VF, the velocity final, or VO, the original velocity, or A, the acceleration, is pointing in the negative direction, plug it in as a negative value, otherwise the equation won't work right. So now let's kind of go back and think of another simple case so we can have a simple equation for it. So we're going to deal with, again, situations with constant acceleration, where once again the motion is only along a straight line, and also if your original velocity is 0. So with those three conditions, we can use this equation. We can find the distance an object has traveled just based on its acceleration rate and the amount of time that that acceleration has been acting. So d is equal to 1/2 at squared. But remember that this equation is only good if the original velocity is 0, if it's starting from rest. So as a quick example, a car accelerates from rest, which just means stopped, at a rate of 5 meters per second squared. So that's representing our A in our equation for 10 seconds. So it's accelerating for 10 full seconds. So this is going to represent our T. At 10 seconds, so after that's all done, what is its velocity and its position? So I'm going to take this equation from earlier. We want to know the V final, so I'll use the original velocity plus A times T. The initial velocity was 0, it was stopped, times the acceleration of 5 meters per second squared, times the time interval T. Do the math, the value turns out to be 50, and the units turn out to be meters per second. We had meters per second squared, but then we multiplied it by seconds. And then to find the distance that it traveled in that time interval, I'll use this equation here. The distance it traveled was equal to 1/2 times the acceleration value times the time interval squared. So then here I just took our 10 seconds squared and I just completed the square. So 10 squared is 100. And seconds squared is seconds squared. So 1/2 times 5 times 100 is 250. And then for the units, we have a meter per second squared times a second squared. So the second squareds really just cancel out. And you end up with meters, which is good because we were looking for a distance. And it made sense that we got meters per second here when we were looking for a velocity. So as a final answer, I might not just give these. For its final velocity, I'll say actually that it was 50 meters per second forwards, because a velocity should have some sort of direction. And the problem didn't really tell me east or west or north or south or any direction, so I just said forwards. I gave it a direction just to do my job. And its position, I'm going to take the 250 and round it to 1 sig fig, because my starting information was really only 1 sig fig. It wasn't very precise at all. So I'll say its position was 300 meters from its starting point. I didn't have a specific origin. They didn't say it was starting from a house or a gas station or anything, so I just vaguely said starting from a starting point. So that would be a nice, complete answer for what is its velocity and what is its position.